Hi, welcome back to another chemistry video. Today we're going to talk about solids, liquids, and gases, particularly focusing on solids and liquids, and we'll be spending the next couple days talking about just gases. So a reminder that matter exists in three states: solid, liquid, and gas. Their differences are influenced by variances in their spacing and the motion of their particles. The reason for the variances in spacing is intermolecular forces. The stronger the forces, then the more likely it is that your substance is a solid or liquid. Less intermolecular forces, you have a gas where particles have very little attraction to each other. So I think we started the year off with this definition. All matter has two distinct characteristics. It has both a mass and a volume. And again, it comes in these three states of matter. Solids, defined by their definite shape and their definite volume. Particles are tightly packed together, vibrate gently in fixed positions, so they're not really moving past each other, they're just vibrating in their spot. And make sure you also realize that this means particles always have motion. If something has a temperature, then particles are having motion. The only exception being is if particles reach the temperature 0 Kelvin, which doesn't exist on Earth, then at that point, particles have no motion. But that is a rare exception and has not been reached before. Liquids have no shape of their own. They're going to take the shape of the container, but do have a definite volume. Their particles are able to slide past each other and freely move. Gases have the most energy. They have no definite shape, no definite volume, and are spreading apart in order to fill the space available to them. And just a reminder that these are the particle diagrams for solid, liquid, and gas. You will not be asked to draw a particle diagram for a solid, liquid, or gas on the AP, but you should have the knowledge of what it would look like in a diagram. Alright, so a little more on solids. Solids really have two categories as in structure. They can have a crystalline structure, which is a regular ordered repeatable 3D structure, similar to the lattice structures that we were talking about with ionic compounds. They also have an amorphous structure, where particle arrangement is not regular or ordered. Examples of amorphous solids would be plastics and I believe gels as well. Most items fall into crystalline, but there are, of course, always amorphous too, that we don't talk about that much in AP chemistry. Solids also have very little energy. They move very little in relation to one another. Again, their particles are just vibrating in pace. They're not really moving past each other like you would see with a liquid and a gas. Liquids. Liquids still have particles very close together like a solid. Unlike solids, these particles are moving constantly and they're colliding with one another. They do have greater energy and therefore greater movement, which is seen with their particles sliding past each other. And since solids and liquids tend to have their particles pretty close together, their volumes are often pretty similar. And by that I mean if you take the solid of a substance and a liquid of the same substance, their volumes are fairly close together. Always the exception, water. Water is, I think, the only substance where the solid is actually going to take up more volume than the liquid. Typically your liquid would take up a little bit more volume, and that's due to water's hydrogen bonding. It forms a unique crystal structure when solid. Properties of solids and liquids. All properties of solids and liquids such as viscosity. So viscosity is measuring how fast something pours. Like for example, honey pours slower than water. That would be an example of viscosity. Surface tension, hardness, all depend on how the particles are arranged and their intermolecular forces between them. Like I said, when liquid particles are more attracted to each other, they have stronger interparticular, meaning intermolecular forces, but whatever type of intermolecular forces that substance has, it's more likely to be viscous. So like honey, molasses, maple syrup, they're fairly viscous. Their particles have stronger intermolecular forces, hence why they pour in a thicker, slower manner compared to something like water or milk, which would have weaker intermolecular forces and hence pour slower. Gases are unique. Their particles are in constant motion. Their frequency of collision, spacing is dependent on temperature, volume, and pressure. Because of their constant motion, there's minimal effects between their particles. There's minimal effects of the forces between their particles, meaning the intermolecular forces shouldn't be affecting particle motion that much. A gas has neither a definite volume nor a definite shape. And again, this means that the particles are able to move freely. And again, we're going to spend quite a number of days after this discussing what should be expected for a gas, what actually happens with gases, and doing some calculations with pressure, volume, and temperature. And lastly, heating and cooling curves. You should be able to read a heating and cooling curve from Regents Chemistry, but I don't think you will have to draw one or interpret one for the AP. But since the different states of matter have particles with differing energies, you can convert between them and figure out how much energy is required in order to do those phase changes. These energy changes, again, phase changes, are quantified and plotted on heating and cooling curves. So something like this. And heating and cooling curves give us a lot of good information. A reminder that when you see a flat curve, or a flat line I should say, this is where temperature is constant, kinetic energy is constant, and a phase change is occurring, so you can see it's labeled with two phases. All the increasing or decreasing lines in the case of cooling off, that's where you only have one phase of matter. These are also useful because you can actually get the boiling point, the melting point of the substance, see the amount of time it takes, and also you can do Q calculations and calculate how much energy was actually required to go through each of these steps. That's all for today's video. Like I said, tomorrow we're going to jump right in with gases. Have a good day.